of the, that's good. A few people will mention this just because of the chat window filling up with really off-topic comments. I'm supportive of it within reason, but I have had a couple of people comment to me privately that they're finding it pretty distracting, and then they kind of lose track of the questions that do rise up from the class. So what I wonder is, for those of you who, that's a really important part of your interaction during class, you can open a Discord window on the side or something. I know you got one going for this course. Oh, someone's streaming a video game on our camera right now. So I am going to stop the video. Does that work? Yeah, it's easy to ignore the chat, but that's a good point. I'm sorry, that was, yeah, don't stream video games live when you're supposed to be in lecture. Like, don't show up if you're not going to pay attention. That's cool too. You can catch the video later. But try and keep it at least somewhat on topic in the chat window. Okay, so we have this. Lecture 3 slides are not on Blackboard. I'll go check and make sure that they are. They should be, so that's a surprise to me. I'll check and make sure that they are. If not, I'll put them up. So we have an acid, carboxylic acid like this. We're going to use an equilibrium arrow. And what we're going to show is that, like, you've seen this a lot, acids dissociate. Sorry, I've already cheated. I've already sketched in the thing I'm going to talk about later this lecture. So thank you for catching that there, Amla. So it's attached to a methyl group. So hopefully this isn't too unfamiliar, this idea that we have an acid and we can dissociate an acid into our carboxylate and NH+. This is acetic acid we have here. It's vinegar. And this is why it's acidic and why it's kind of bitter, is because you can taste CH+. It's a little bit more complicated than that, but you know, we'll keep it simple. So this, what I've drawn here, is an equilibrium arrow. I'm sure there's probably too many bumps in my U there. I'm sure a lot of you have seen equilibrium arrows before. What this means is the relative size of the arrow indicates which way the direction is going. Depending on the conditions, I could have drawn this either way, depending on what else is going on in the solution. I arbitrarily made the top arrow bigger. So what this means is this equilibrium, and I hate writing equilibrium because of all these bumps over here in the way I do cursive. So I'm just going to write that as equilib lies to the right. And so what that means is, if this thing is in solution, there's more of the stuff on the right than the stuff on the left, because that's how I've drawn that arrow. Okay. Now, what we have here is I've drawn one structure there, and then if I can figure out how to do this with my changing color, I'm going to try and change color using my, there we go. And if I draw another structure here, I can draw the acid like that. Now, a question could be, are these the same molecule or are these different molecules? Like, clearly I had a double bond going to the up oxygen over here, and now I have a double bond going to the right oxygen over there. But I can't tell there's two oxygens because they're both oxygens. Yeah, same, since you can just rotate, that's true. But there's something even more like that, and that's where we're coming back to this idea of resonance, that you don't even need to rotate. these are exactly identical molecules. And so what we can say is that they are equal ways. This is a resonance arrow. They are equal ways of drawing the exact same molecule at the same time. Because which of those is more, neither of those is more right. They're absolutely identical. If you try and look at the energies of those two things I've just drawn, they're absolutely identical. And the way we go from one to the other, that's just with the rotation. I'm going to delete that arrow because it's a little confusing. The way we go from one to the other yes, there is a C here. Again, sorry, I'm getting so I have to unlearn myself. Is these electrons come from the oxygen. They go to the space between the two carbons to generate a double bond. But if we do that, and if we draw just the result of that, so I'm just going to draw the result of what I just drew. And if we don't pay too much attention, we're going to get to that. If we don't pay too much attention, we could draw that. So how do we get that? Well, you can replace all of these lines I've drawn with 2 electrons. And if we do that and we count the number of the formal charge on this middle carbon of this carbon up there, it would be, well, 4 minus 10 electron minus 1/2 of 10, because there are 10 electrons in bonds, which would be -1. I drew, this whole thing is wrong. Everything I just drew up there is horribly wrong, and I'm glad people are calling me out on it. So this is wrong because our carbon is making 5 bonds. That is absolutely impossible. Carbon only has 4 orbitals. You can only get 4 groups of electrons over there. It's in the second row. You've got 3 p's and 1 s. You've got 4 orbitals. That's all you got. You can't make 5 bonds because 5 bonds will need to use 5 different orbitals, and carbon doesn't have 5 different orbitals. So it's not even an intermediate. This thing just doesn't exist. Is not a thing. It's not intermediate. It's not a transition state. This is not a thing. It is, you know what? I could write wrong. Actually, I'm going to. Wrong on there. The whole thing is wrong. But the formal charge, if that molecule could exist, the formal charge will be a negative charge on the carbon. No lone pairs or anything, just a negative charge on the carbon. That's wrong, though. I can't make something with 5 bonds. So how do I solve that problem? Well, I can break the carbon-oxygen bond. And so again, what I'm doing, double bond. So what I'm doing here is I'm using the 2 electrons in that double bond, and they're leaving the space between the carbon and oxygen where they're making a happy little bond, and they're going on to the oxygen. And so if I do my electronic counting here, I now have that oxygen-carbon double bond, and I have this carbon-oxygen single bond. And there's a negative charge. And the positive charge, the resulting positive charge is over here on the H+. It's still floating around. It's over here. So these 2 structures are resonant structures of one another. I haven't moved any atoms. No atoms have moved. No single bonds have broken. What we have done is we have broken double bonds, and we have moved electrons around in pi systems, which is what we were talking about at the end of last class. And so these 2 molecules are not flipping back and forwards between one another. It's not like it's switching real fast. It's these 2 things are different representations of reality. And together, they merge together to make the real structure. So how do we represent that? Well, the real structure has a partial negative charge on that oxygen, a partial negative charge on that oxygen, and a partial double bond between the carbon and both of the oxygens. Yeah, I'm going to talk about that a lot in a moment. We're going to get to all of that. I just want to make sure we're all on the same page on this. So, sorry, the question. I'm going to try and read the question out loud before I answer the question because somebody pointed out that's really confusing in the video. Somebody said, I get that resonance is the moving of electrons, but can you explain why we do this and when we know how to do it? Absolutely. I just want to know how the HL was broken. It breaks. It's a very weak bond. H plus comes off, H plus goes on. H plus comes off, H plus goes on. All OH bonds, the H is constantly coming on and off. It's why, you know, we have the Kw for water, where water is in equilibrium with the OH minus and the H3O plus. And it's entirely because that bond has a certain amount of energy stored in it. And probability being the thing it is, that energy is not infinite. If it was an infinite amount of energy stored in that bond would always be intact, no matter what. But it's quite a weak bond. And so given enough molecules, some of them break the bond and some don't. And depending on what the conditions are, that bond becomes quite easy to break. Okay. Yes. So I just said we have a partial double bond. What is a partial double bond? So if we look at, this is something, you know what? This is something where it is handy having a internet machine right in front of me because I can look something up as I'm talking. Bond length, carbonyl. So in a ketone, or an aldehyde like this bond length here is around 123 picometers. Picometers is a stupid unit of measurement, so we're going to change that to 1.23 angstroms, which is 1/10 of a nanometer. And I want to find out, just looking this up. So in a single bond, like a single alcohol, like this, like methanol, that length is about 1.30 angstroms. You know, this isn't a huge difference, right? Like, come on, we're talking 0.07 angstroms, but it's meaningful. There's a difference. In a carboxylic acid, carboxylate, both of these bond lengths are the same. They're 1.26 angstroms. So they're in between a single bond and a double bond. So when a single bond is longer, it's 1.30, the two things aren't held as tightly together. They've got a single bond between them. Double bonds, you tighten them up down to 1.23. But in a carboxylate like this, it's intermediate. So it's not as long as a single bond, it's not as short as a double bond, it's kind of in between, and they're both the same. But the way I've drawn it there, they're not both the same. One's double bond, one's a single bond. But that's because that's not the case. Like, that's the way we've drawn it, because that's the only way we can draw Lewis structures. We have to draw the bonds somewhere. But what we need to know is that that is the resonance structure of the other one. And they're absolutely equal in energy. There's no difference in the energy of those resonance structures. If I pretend that those things are pure things that are static and stay there, and I look at those and go, those are exactly the same thing. It's exactly the same energy. You don't need to memorize any of this shit. You don't need to memorize any of these numbers. Sorry, I swore. I've really been trying not to. You don't need to memorize any of these numbers, any of these angles, any of this stuff, because you're going to write all your exams open book. Now, if you want to write these things down in order so you have a nice organized system for that, great. That's awesome. What's the purpose of pointing out the bond lengths? I'm trying to show that this carboxylate, these bonds are not double bonds. They're not single bonds. They're in between. So double bond is 1.23 angstroms. A single bond is 1.3 angstroms. These are 1.26. They're kind of in between a single bond and a double bond. So they have some of the character of being single bonded. They have some of the character of being double bonded. And so that means that we have this, where's my cursor? It is in the wrong spot. We have this resonance hybrid, going back a slide. That's what this is called. It is what our little brains can try to understand of reality, where these are a partial double bond between both of these, but not a full double bond. Okay. So there's a question here going in general, is a shorter or longer double bond more stable? Or a shorter or longer bond more stable? This is a very it's a really complex question. What I'm going to say is a bond with more electrons involved is more stable. And so a double bond has 4 electrons there. A single bond has 2. So a double bond isn't like a special thing. It is a single bond plus another bond. It's 2 different bonds. So it has all the energy of the single bond plus this extra energy benefit of a double bond. So it's not like a unique special thing. It's kind of duplicated. You know what? On the exam, you are not going to be tested on any of this. This is the basic stuff that you are going to be using to do everything. This is your toolkit. Like, I'm not going to test you on what is a screwdriver. I'm going to test you on, can you go ahead and build this thing? And you're going to need to use screwdrivers. So you need to know what a screwdriver is to build something. Yes, you're at, nope, the charges are right. The oxygen, if you count the number of electrons on these, so this guy here has got 6 electrons unpaired, 2 electrons in a bond. You do your math, you go, okay, 6 minus the 6 unpaired is 0, minus 1/2 of 2 is -1. So this is negative. This guy is neutral because the valence of oxygen is 6. 6 minus 4 unpaired electrons is 2. 2 minus 1/2 of 4 is 2 minus 2, which is 0. So the charges are correct. But thanks for making me check, Quinn, because I would mess that up. That sounds like exactly what you do. The closer you get to the board or drawing things, the stupider you get. It's like the first rule of organic chemistry. Yeah, see, this is why I will try and draw in all the lone pairs right now. I was sloppy on that. There we go. Okay. So let's look at another example. So one question I can ask is, I am going to draw a molecule. Okay. So what we have here is now obviously something's missing, you know, okay, I'm gonna have a chloride that's kind of hanging out over here. It's dissociated, it's left. Let's not ask too many questions about that because this is a proof of concept thing. And it's true, it actually would in this case. I have this molecule, so what I have here is I have a carbon that only has 3 bonds. And it's got a positive charge because carbon is supposed to have 4 valence electrons. And if all it has is 3 bonds, it's 4 minus 1/2 of 6, 4 minus 3, that's +1. That makes sense. And nitrogen's supposed to have 5, and I can quickly see that nitrogen's making 3 bonds. It has a lone pair. That's nitrogen's happy place. That's where nitrogen wants to be. So I can think, can I draw any resonance structures of this molecule? And again, a resonance structure is I'm just moving electrons. I can't move any of the atoms. I can't rotate any of the bonds. I can't break any single bonds, but I can break double bonds because double bonds are easy to break. They're much weaker. And I can move lone pairs around. Double bond between C and N, perfect. So I'm allowed to do that because if I count at the end of what I get here, my carbon's making 4 bonds. That's fine. It's allowed to make 4 bonds. I'm not trying to make carbon make 5 bonds like I tried to do last time, which did not work, right? We wrote wrong all over it and stuff. My nitrogen's making 4 bonds. It's not a happy nitrogen, but it's possible. It's second row. It can do that. And if you count the formal charges, I'm going to leave that as an exercise. You'll find that the nitrogen is +1, the carbon is neutral. What we've done here is we've moved the electrons from the nitrogen lone pair to the space between the carbons and the nitrogen. And that's what that arrow means. It goes from the electrons to where it's going. So if we look at the resonance hybrid here, to draw the resonance hybrid, the first thing you do is you draw in all the single bonds that never break. Draw all the bonds that don't break ever, whenever in any of your resonance structures. It depends what the question asks, Suhaib. So Suhaib said if we were given a question like this, we have to show the arrow showing where we took the bonds from. Depends what the question asks. And that, my answer to your question there is going to make a lot more sense in a few lectures. Yeah. Yes, good question. So let's think about that. So I'm going to draw a resonance hybrid here. What I'm saying is there's an overall positive charge on that molecule. I'm saying, by putting it in brackets, I'm saying this is not a real Lewis dot structure. And this is not a real Lewis dot structure because I have a partial bond in there. And Lewis dot structures have electrons in specific places. And I'm being cagey about where my electrons are. Note that I'm not drawing in a partial lone pair. We just don't do that. And the more I think about it, the more I don't understand why we don't do that, but we don't. We draw in a partial double bond. I guess we just don't have a way to draw a partial pair of dots. Now, if what we have is we have 2 different types of positive charges. In the last case, the 2 oxygens were equal. In this case, these are clearly not the same atoms. This is unequal. So there's a couple things you can think about here. Actually, you know what? Well, I pulled the class, but I hadn't. I wish I had figured out how to use the pull function, but I didn't, because of course I didn't. I want you to, in your heart of hearts, think about this for a second and think, where do you think the bigger positive charge is on, the carbon or the nitrogen? I want you to come up with a reason why. Where do you think the bigger partial positive, sorry, Suhaib, thank you for asking. Where do you think the bigger partial positive charge is, on carbon or nitrogen? Okay, this is great. I've got first 2 answers from Janik and Victoria are against each other. One says carbon, one says, oh, we're all over the place. This is awesome. Nobody's yet said oxygen, which is good. Oh no, okay, there we go, oxygen. Okay. It's on the nitrogen. So this is something that people make a lot of mistakes on, and you are right. When I saw somebody say, so Janik said carbon I'm sorry, I really hope I'm getting your name right. Carbon, because nitrogen is more electronegative, so electron density lies there. You're absolutely right, and you're wrong in this case, and we're going to discuss why. But your logic is perfect. It's just you're missing something. Other people have said nitrogen with no explanation. So what we want to think about here is what I'm basically asking with this question is which of these two resonance structures contributes more structure. I'm going to write kind of Hebrew and leave out the vowels occasionally. Well, you know, English and Hebrew. Contributes more to the resonance hybrid. So that's the question I'm asking. Another way to think about that, what that means is which is more stable. Okay, so people are saying B, and I that obviously it's B because I said B was the answer. So that's good. Great job. And I like where Victoria kicks in, says the octet rule. And she's right. So what we have here is there are different types of positive charge. This nitrogen is formally positive. Yes, you do your electron accounting, you get +1. That's what happens. But let's look at its electron configuration. It's got 8 electrons around it. That's a happy nitrogen with 8 electrons around it. If we look at this carbon up here, this is really positive. There's nothing formal about it. It's only got 6 electrons around it. And it's a second row element. It wants 8. So here's a little rule that we have. It's the octet rule. Things want to be noble gas configuration. They want their 8 electrons. And so in the bottom case, the nitrogen has its 8, the carbon has 6. Now, everyone who said that the carbon should have the positive charge because it is the more electropositive or less electronegative element, you're right. If we were comparing a carbon with 6 electrons and a nitrogen with 6 electrons, you better believe that positive charge is on that carbon. But we're not comparing that. We're comparing a carbon with 6 electrons and a nitrogen with 8 electrons. And so the octet takes precedence. And then I'm actually going to call this rule number 4. Positive on electropositive. Negative on electronegative. Atom. We're going to get to rules number 2 and 3. We're going to get to them as we fill them in. We're going to come back and show that. But these are the order of importance. What I'm basically saying is your octet's your most important thing. So N is more positive because it's sharing. N is positive in B because it is positive. Count the electrons, it's positive. N is in a resonance hybrid, the majority of the positive charge rests on N because structure B is more stable than structure A. Structure B is more stable than structure A because in structure A we have a carbon with 6 electrons, which is bad. In structure B we have a nitrogen with 8 electrons and positive, which isn't great, but everybody's got their full octet. Yeah, that's negative and positive. It's a V. Negative. Sorry. Positive. So rule number 4 is put the positive charge on the electropositive atom, put the negative charge on the electronegative atom. That only comes into it if you don't solve your problem earlier. And we did. We're comparing A and B. We hit rule number 1. We want octets. B, everything has its octet. A, not everything has its octet. B is more stable than A. No, in resonance structure A, the nitrogen is not positive. It's completely neutral. It's got 5 electrons. Bennett asked me if the nitrogen, sorry, I'm going to call you out because it's a private question. Should have gone into the whole thing. In structure A, the nitrogen's got 5 electrons, 5 valence electrons. It wants 5 valence electrons. It is neutral. Yes, we're calling it rule 4 because it's less important than rule 1. We're going to go in order. These are all kind of like tiebreakers. So it's like, okay, well, if we can't break the tie on rule number 1, we go to rule number 2. If we can't break the tie on rule number 2, we go to rule number 3. Okay, so let's have an example where we need rule number 2. So let's say we have, this is acetone. It has single-handedly changed the texture of my skin because I've just covered so much of my skin in acetone over the years. Sorry, I am going to draw on the carbons. I'm really sorry. And there's a carbon at the vertex here where the bonds meet. What time is it? 2:05. So a moment ago, a couple slides ago at the beginning, I said, hey, look, this bond length is 1.23 angstroms, this double bond. Well, a carbon-carbon double bond is more like 1.18 angstroms. So this is already a little bit longer. And that's because I lied when I said it was double bond. Well, no, I didn't lie. I sort of lied, I guess, a little lie. And that's because it's not an equal double bond. We have a resonance structure where we can move the electrons from the double bond onto the oxygen. I guess this isn't one example where we break the octet. Everyone does still have an octet. Yeah, I fibbed. I fibbed. Yes, we'll do that. In the structure with 2 oxygens and CH3, back in the acid, that was because it actually was missing an H+. It was actually like a negatively oxygen. It was just, yeah, that H+ had wandered off. And so suddenly this oxygen had an extra electron. Here, nobody's got an extra electron. This is a neutral molecule. That was not a neutral molecule. So if we're looking at this, there is a resonance hybrid. We don't normally draw it because it's kind of, we normally just draw the normal structure. I have there on the top left for acetone, but it's not a completely accurate description. Notice there's no net charge on the molecule. We draw a pretty small delta plus and a pretty small delta minus on these. And I'm going to say, well, which of these is a bigger contributor to the, I can move the double bond to one of the oxygens in the first example. Back with the acid manual. Yeah, you could, and we're going to see, and exactly because Quinn has just given us rule number 2. So, which of these is more stable? So, rule number 2 is minimize charge separation. It's actually rule number 3. I'm going to try and think of an example for rule number 2, because there's something a little bit more important than that. So rule number 3 is minimize charge separation. We want to keep, this actually breaks rule number 1, of course, too, right? Because that carbon there has a positive charge. It doesn't have its full octet. That tells you that's not good. The oxygen does have its full octet in all cases. Yeah, it's the third rule. Rule number 2 actually comes from, we actually saw that last class. But you know what, we'll do a really simple version of it. So if we're looking at what the resonance structures are of this one, I've got one here. This is clearly just a really bad resonance structure. Like you're comparing it to the starting material and you're going, this makes no sense. You don't have a negative, you don't have a charge on an electronegative atom. You made a C plus positive, like the whole thing just, this is just awful. I explained rule number, I'm going to explain what rule number 2 is. We haven't talked about what rule number 2 is yet. And I'm going to write all the rules in order. But we have another resonance structure, and it's not as obvious. And again, I'm learning my lesson about how to use my mouse. Oops. I'm sort of learning my lesson about how to use my mouse. And that's if we do a homolysis, which means breaking the bond equally. This is actually called, well, I guess we're not really breaking bonds, but we're moving electrons around. Heterolysis, we're breaking a bond unequally. Here we're breaking it equally. And so I've drawn single arrows with single hooks, and that means one electron is moving. So here, if I'm looking at the rules, I've broken the octet rule here because each of those carbons only has 7 electrons. Mohammed, that's a great question. We're going to come back to that. We're going to end on that thought at the end of the class. But this is rule number 2 is maximizing the number of bonds. So these things often go together. And we're going to see some complex examples where we're having these things interplay. It really is. I hate radicals. These are free radicals. They're awful. They're disgusting. You're right. There's a reason organic chemists were scared of radicals for about 60 years. So homolysis is breaking the bond equally. And what we want to do is we want to maximize the number of bonds. And the reason why, one of the reasons why A, B, C, one of the reasons why A is so much more stable than C, there's no charge separation, but we're maximizing the number of bonds. We're keeping everything against full octet, and we're maximizing the number of bonds. Homolysis is homo as in same, and so you're lysing the same way. So the end results are the things are identical. So each one is getting one electron. Heterolysis is you're lysing differently. So you're breaking differently. That's what lyse means. And hetero is different. And so you're moving two of the electrons onto one side. So one side is negative, one side is positive. Okay. Is C more stable than B? Yeah, it is. Because in C, you have the same problems with not complete octet for all atoms, but in B, you have that charge separation. And in C, you don't have that charge separation. And in both cases, you have the same number of bonds. So somebody has pointed out this question, why do atoms do this? Why are molecules doing this to me? Why is this happening? I don't want this to happen. Wouldn't it be nicer if everything was frozen in place? And I think the way to think about it is let's go back to acetone. And so this is where I'm going to change how we're drawing things. This is equal to that. So what this is claiming is that lines end in carbons with the right amount of hydrogens. And then all vertices are carbons with the right amount of hydrogens. And by right number, I mean the right number to make them neutral. We're going to do this because I can draw these a whole lot faster. So another example is if we have CH3, CH2, CH2, CH, CH3, CH3. That's equal to that, where that's A, B, C, D, E. If I could draw an E, F. So A, B, C, D is where they branch, E, F. Now I know for like probably 70% of you, 80% of you, you've seen this before. This is not new. This is not original. For some of you, this is a completely different way of expressing things. You just need to keep track that there are hydrogens on there. That gets a little bit confusing, which is why I want you to make sure you know how to do the formal charge stuff. At this point, I'm going to try and remember to draw in the lone pairs where they're relevant. But I'm going to stop doing that at some point too. Yeah, so why resonance? Electrons are always moving. That's exactly it. Electrons always want to move. So what you're basically saying is if a molecule can have its electrons flow, if the electrons aren't trapped in one place, if they can be in lots of different places, that's what they want to do. So like you're looking at acetone, you go like, there's nothing wrong with you up here. You're like a happy molecule. Why would you even want to consider doing this? Like, why would you do that to that poor little carbon in the middle there and make it positive with 6 electrons? I know that's bad. You shouldn't do that to that carbon. It's like carbon abuse. It's not like making a carbon with 5 bonds. That's like beyond the pale. That's carbon torture, or Dr. Trent torture. Or, well, torture for you because I'll take marks off. But that's ugly to me. It's like an abomination. But it's possible. And the reason it's possible is because it gives the electron some freedom of motion. And motion is the wrong way to think about it because they're not really, like, they're waves, right? They're not really particles. And so motion isn't what they're doing. But the electrons are able to occupy more possible states of being, more possible energies. And when you can occupy multiple different energies at once, you're actually lowering the overall energy of the system. So resonance is always stabilizing. It is always, and here I am making a moral judgment about stability of atoms, but I'm going to say that lower energy is good. So resonance is always good. It always stabilizes. Okay. So we have 4 rules of resonance. When comparing structures. I'd love to say my handwriting is worse because I'm writing on a tablet on a computer, but it's not. My handwriting is just this bad. Everyone has an octet. Number of bonds is maximized. So why is everyone has an octet's important? Because every atom wants to have 8 electrons around it. If an atom has fewer than 8 electrons around it, and it could have 8 electrons around it, you're leaving energy on the table. You're basically having 8 electrons around you means electrons are in orbitals. Those orbitals are lower in energy. We're going to get to all of this. And that's going to make a little bit more sense later. But you're basically just leaving free energy lying around that you're not using. And molecules don't do that. Molecules want to use the energy if they can. Number of bonds is maximized. Again, if you have electrons in a bond, they're lower in energy than if they're in a lone pair. So electrons want to be in bonds. They do not want to be in lone pairs, and they definitely do not want to be single electrons sitting as radicals. Charge separation is minimized. So ideally, you have no charge separation. Like all your charges are neutral. If you have charge separation, you have them as close as possible. You have the plus, and minus as close as possible. And 4, positive charge on electropositive atom, negative charge on electronegative atom. So that's it really, actually. I think that basically sums up almost all of charge stability. Essentially, that's the course. Now we're going to use this in a whole bunch of different ways. We're going to talk about, we're really going to go into detail in it. But when it comes down to it, that's really organic chemistry. Molecules want their octet. Charges do not want to be charges. Bonds want to be made unless there's a really good reason to break them because you're making something else. You're making something really stable. And you want to put your positive charges on your positive atoms and negative charges on negative atoms. Yeah, final exam next week. So we're at 2:22, following all the rules of, in-class lectures. I guess you have 10 minutes to close this Zoom window and open your next Zoom window. But we'll leave it there for today. And starting next class, we're going to start talking about acid-base chemistry, and we're going to be talking about charges, and we're going to be talking about resonance, because all chemistry is driven by trying to get things stable. Everything wants to end up in perfect stability, and everything's trying to move towards that point. Like the entire universe is trying to move towards stability. So, and chaos at the same time. That's enthalpy and entropy. And we're just going to be talking a lot about enthalpy right now. So we're going to be discussing how we can apply all these things to acids and bases. Is an overall resonance structure more stable than a neutral molecule? Yes, in that the neutral molecule doesn't exist, right? The neutral molecule is one way of drawing the most common part of the resonance, the most common contributors to the resonance structure. And for something like acetone, it's so close. Like the neutral molecule has so like 99.9999% of the contribution to the resonance hybrid, but it's not 100%. And so the resonance hybrid is slightly more stable than just drawing a neutral molecule. But the neutral molecule doesn't exist. It's a simplification of the resonance hybrid. So charge separation is if you have a plus and a minus in one resonance structure and another resonance structure has no charges, that's better. No charges is better. And if you have a plus and a minus really far away from each other and another resonance structure you have the plus and a minus closer, that's better. Everything on resonance. And I would read that resonance is really hard. This is a really hard concept. And we're going to start talking about molecular orbitals and atomic orbitals, and that's going to help a little bit. I'm trying something different this year. I'm putting this thing up front and getting this thing out there early so you can start thinking about it from multiple different angles. Read the textbook, look at Wikipedia, look at other textbooks, look at everything. This is a really complex idea because what I'm telling you is that static bonds don't exist and that everything is a hybrid of multiple different contributors. And that's just weird. It is. It just is weird. And so right now we're going to leave it at pi systems. And for this course, we're going to leave it in pi systems. We're going to leave it in double bonds. But in reality, it's in single bonds as well. And everything is really confusing. And it is what it is. Yes, naming game. I am putting that up there. Thank you, Suhib. I am doing that. I'm making a note. Post naming game link. When we have a partial bond with oxygen, how many lone pairs does the oxygen have? That question cannot be answered. One resonance structure has 2 lone pairs, for example. The other one has 3. The resonance hybrid is intermediate between them. That's why I didn't draw the lone pairs in. Or I would draw in only the ones that are always there. And I left the lone pair that's not always there, didn't draw it in. It is partially there, partially in the bond. So resonance is introduced in chapter 1 in the textbook. It is then scattered throughout the entire textbook because we're going to constantly come back to these ideas. Yeah, I will start a discussion thread on the Blackboard. Thank you. I'll put a forum up there. Yeah. Okay. Recommend it. You know what? Sure. I'm going to pull up. I don't know if I have my video on. No, I don't. Oh, that's good. Okay. So I have the textbook here in front of me. And I have the table of contents here in front of me. And I'm looking up. Oh, there's a more detailed one. So on page Roman numeral 5, section 1.8. So page 26 to 32 talks about resonance. But we're going to be talking about resonance in chapter 5 and chapter 6 and chapter 7, chapter 8, chapter 9. Actually, everything's about resonance. This course is really about resonance and it's about charge stability. So we're going to constantly be practicing these things. If it didn't all make sense today, that's fine. Yeah, you can use any textbook. You just need to have the Mobius that is associated with this course so you can do the online assignments that we're putting up there. but you can use any textbook. I like this one the most, which is why I assigned it. It's slightly cheaper than Cardi, which is another reason I assigned it. But that's up to you for this one. The first, it's in the syllabus. It's sometime in October. Yeah. Yeah, it's normal for your brain to be exploding around now. No, it is. We are going to be touching on reactions, but if you don't have the basics, you can't do anything with the reactions because we're going to be trying to explain why the reactions do the things they do. So my interest in reactions is why do they happen? I can give you long lists of things and say, hey, memorize all this stuff, but it's kind of pointless. So we're going to be focusing on why reactions occur. Why is this occurring? Why this and not that? And comparing multiple different things that could occur and why this one is the one that's happening. Yeah, graded assignments are going to be on Mobius. Yes. Okay. And that's what it says in the syllabus. I'm going to start ignoring questions that are in the syllabus. Okay. Have a good night, everyone. I'm going to post these slides. I'm going to make sure that the slides from the last lecture, for whatever reason, something's happened, make sure that's okay. And I'm going to post the link to the naming game. Okay, I'll talk to you guys later. Have a wonderful weekend. See you Monday.